4 billion miles from where you're sitting right now, a telescope built to stare at galaxies that existed before our sun even formed, somehow managed to pick out a single tiny world buried in the glare of its own moon. And when scientists finally pulled that signal apart, what came back was something almost nobody thought Webb would ever be able to see. Stay with me, because I'm going to walk you through exactly what James Webb just confirmed about Pluto, and why so many researchers spent years assuming this particular observation simply could not be done. And if you want more of these deep dives into real published space research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the outer solar system that most people have never heard about. To understand why this observation was considered so difficult, you first have to understand what Pluto actually is and where it sits. Pluto was discovered in February of 1930 by a young observatory assistant named Clyde Tombaugh, who spent months comparing photographic plates of the night sky, hunting for a single point of light that moved against the fixed background of stars. He found it, and for the next 76 years, Pluto was taught in classrooms as the ninth planet, a distant icy world at the edge of everything we understood. Then, in 2006, the International Astronomical Union voted to reclassify it as a dwarf planet, a decision that still sparks arguments among astronomers today. But whether you call it a planet or not, Pluto never stopped being strange, and it never stopped being almost impossible to study properly from Earth. The core problem is distance combined with company. Pluto sits roughly 3 billion miles from the Sun on average, so faint that even in Hubble's best images, it appeared as little more than a fuzzy, pixelated blob. Worse, Pluto doesn't sit alone out there. It has a companion moon named Charon that is unusually large relative to its parent world, more than half of Pluto's diameter, and the two bodies orbit so closely together that from any telescope on or near Earth, their light essentially blurs into a single point. Trying to isolate Pluto's faint heat signature from Charon's heat signature at that distance is a bit like trying to tell two matching candle flames apart from across a football field at night through fog. For decades, that simply couldn't be done with any real precision. In July of 2015, NASA's New Horizons spacecraft finally gave humanity its first real look, flying past Pluto after a 9.5-year journey and capturing images during a single narrow flyby window that lasted only a few hours. There was no orbit, no second pass, no do-over. What it captured rewrote the textbooks in an afternoon. A massive pale plane shaped roughly like a heart stretched across part of the surface, smoother and younger looking than the ancient cratered terrain around it. Mountains built from water ice, frozen so hard in Pluto's extreme cold that it behaved more like solid rock than anything we'd call ice on Earth, rose thousands of feet into a strangely layered, hazy sky. That haze turned out to be the detail that would occupy scientists for the next decade. New Horizons could photograph the haze, but it could not tell researchers what the haze was actually doing to Pluto's climate. A single flyby captures a snapshot, not an ongoing story. And this is exactly where the difficulty starts to make sense, because what scientists needed next wasn't another photograph. They needed a way to read Pluto's temperature and chemistry directly, continuously from Earth's neighborhood, without ever sending another spacecraft on a decade-long one-way trip. On paper, that request sounds almost unreasonable. You're asking an instrument sitting nearly 1 million miles from Earth to resolve the thermal glow of a dwarf planet smaller than our own moon, sitting 4 billion miles further out, while filtering out the heat signature of a nearly as large moon practically glued to it in the sky. Multiple research teams had tried versions of this measurement with earlier infrared telescopes before Webb ever launched, and they kept coming up empty, not because the effect they were looking for didn't exist, but because no instrument had the resolving power and sensitivity to cleanly separate the two overlapping signals. That changed once the James Webb Space Telescope's mid-infrared instrument came fully online and was calibrated well enough to take on a target this faint and this crowded. Around 2022, once engineers were confident in the instrument's precision, Webb turned its enormous gold mirror toward Pluto for the first time. And this is the part that genuinely surprised a lot of the researchers involved. Webb didn't just detect Pluto, it detected Pluto's atmosphere behaving in a way that broke the pattern seen on every other hazy world we've ever studied. Here's the background you need to appreciate why that mattered. Back in 2017, a planetary scientist named Shi Zhang at the University of California, Santa Cruz, published a theoretical prediction that struck many of his colleagues as counterintuitive. On Saturn's moon Titan, which also has a thick hydrocarbon haze, that haze traps heat and warms the atmosphere underneath it, similar to how a blanket works. Zhang proposed that Pluto's much thinner haze might do the opposite. Instead of trapping heat, the tiny haze particles would absorb sunlight during the day, and then radiate that energy back out into space as infrared light faster than Pluto's razor-thin atmosphere could ever hold onto it. In other words, the haze wouldn't be acting like insulation. It would be acting like an active radiator, constantly bleeding heat away from a world that barely has any heat to begin with. For years, nobody could test that idea directly because no telescope existed that was sensitive enough to measure it. Then, using data gathered by Webb once it was capable of isolating Pluto's signal from Charon's, a research team led by astronomer Tanguy Bertrand at the Paris Observatory carried out exactly that measurement. Their results, published in the journal Nature Astronomy in 2025, confirmed almost precisely what Zhang had predicted 8 years earlier. Pluto's upper atmosphere really is being actively cooled by the haze, particles suspended inside it, and the measured temperature came in roughly 30 degrees Fahrenheit colder than earlier models had assumed. Researchers are now describing this as a genuinely new category of planetary climate, a self-refrigerating atmosphere unlike anything else confirmed anywhere else in the solar system. Pluto isn't simply cold because it's far from the sun. It appears to be actively working to make itself colder, and scientists are still mapping out how far the implications of that reach, including whether similar hazes might be quietly shaping conditions on other distant hazy worlds like Neptune's moon Triton. If you're finding this as strange as I did while pulling the research together, drop a comment and let me know, because it genuinely helps me figure out which space stories are worth digging into next. There's a second layer to this story that connects directly back to the haze, and it involves chemistry rather than temperature. Even the extremely faint trickle of sunlight that reaches Pluto carries enough energy to break apart methane molecules high in its atmosphere. Those broken fragments don't just disappear, they recombine into heavier compounds called tholins, reddish-brown organic particles that slowly drift downward and settle onto the surface below. New Horizons caught early evidence of this process back in 2015, and Webb's newer observations have helped refine exactly how the cycle unfolds and how quickly. The detail that tends to stop people in their tracks is what tholins actually represent. They belong to the same broad family of organic molecules that some scientists believe may have rained down onto early Earth billions of years ago, potentially supplying some of the raw material that eventually contributed to the chemistry of life here. On Pluto, that same basic process has apparently been running for roughly 4 billion years, a slow and continuous snowfall of biologically relevant molecules landing on a world simply too frozen for any of it to ever ignite into something alive. To understand exactly how cold that surface actually is, it helps to look at the raw numbers. Sunlight reaching Pluto is roughly 1,000 times fainter than sunlight reaching Earth, meaning even high noon out there would look closer to a deep twilight here. Surface temperatures generally sit somewhere between about -387 and -369 degrees Fahrenheit, more than 250 degrees colder than the coldest temperature ever recorded anywhere on Earth's surface. At those temperatures, nitrogen, the same gas that makes up most of the air around you right now, freezes completely solid and becomes part of the landscape. Webb's observations didn't stop at Pluto itself. Because Charon sits so close by, and because separating the two signals was the whole technical breakthrough that made this research possible in the first place, scientists were also able to get a clearer look at Charon than ever before. Charon's most striking feature has always been the deep, reddish-brown staining that covers its north pole, a color that stands out sharply against the otherwise unremarkable gray-white water ice covering most of the moon. Researchers had suspected for years that this coloring was connected to material escaping from Pluto's atmosphere, but they lacked the tools to confirm it directly until relatively recently. The mechanism turns out to be tied to Charon's extraordinarily long seasons. Because of how Charon is tilted as it orbits alongside Pluto, its northern polar region spends multiple decades in complete darkness at a stretch, with no sunlight reaching it at all during that time. That makes the pole an extremely effective cold trap. Methane molecules that escape Pluto's thin atmosphere drift across the roughly 12,000 miles of space separating the two worlds, get pulled in by Charon's gravity, and freeze solid onto that permanently dark polar surface simply because there's no warmth available to keep them as gas. They accumulate there for years, sometimes decades, until sunlight finally returns to that part of the moon. When it does, ultraviolet radiation and cosmic rays don't just melt the frozen methane away. Instead, they break the molecules apart and reassemble the fragments into heavier, more complex reddish compounds, essentially locking that dark coloring in permanently. It's a genuinely strange partnership between two worlds, a slow, ongoing exchange of atmosphere and color that appears to have been running quietly since long before either object had a name. It's worth pausing on just how demanding this kind of measurement really is from an engineering standpoint. Webb's primary mirror spans more than 20 feet across, built from 18 hexagonal gold-coated segments that work together as a single enormous light-collecting surface. That size is precisely what allows the telescope to achieve the angular resolution needed to distinguish two objects sitting so close together in the sky. Even then, Pluto and Charon appear as barely more than a single smudged point from Webb's vantage point, and separating their individual thermal signatures required extremely careful calibration, along with modeling work to subtract out exactly how much of the detected heat belonged to each body. Earlier infrared observatories simply didn't have the combination of mirror size and detector sensitivity to pull that apart cleanly, which is part of why so many scientists assumed a measurement like this wouldn't be possible until a dedicated new mission physically returned to the outer solar system. Instead, Webb managed to do it from nearly 1 million miles away, without ever leaving the vicinity of Earth. In 2224, a team led by researchers Silvia Protopapa at the Southwest Research Institute used newer infrared data to confirm the presence of both carbon dioxide and hydrogen peroxide frozen directly onto Charon's surface, a combination that had never been confirmed there before. According to the published research, the carbon dioxide most likely originated from underground material exposed by impact craters, while the hydrogen peroxide appears to have formed gradually through years of radiation striking Charon's water ice and rearranging its molecular structure. It's a small detail in the bigger picture, but it adds yet another layer to a moon that keeps turning out to be far more chemically complicated than its plain icy appearance would ever suggest. Now picture, for a moment, what it would actually be like to stand on Pluto's surface, because the details are almost hard to process. The sun would still be visible, but only as an intensely bright point of light, smaller than a pinhead held at arm's length, giving off essentially no warmth and no meaningful glare, faint enough that you could look directly at it without discomfort. The sky around it would sit in a permanent grayish-blue gloom, thick with haze, never fully bright and never fully dark, just an unchanging dimness. The ground beneath your feet wouldn't behave anything like ice does here. At nearly 400 degrees below zero, water ice stops being slippery, and instead behaves closer to solid rock, hard enough to ring almost like metal if struck. And fixed permanently in the same spot in the sky, never rising or setting, Charon would hang there, unmoving, because the two worlds are locked so tightly together gravitationally that each one always shows exactly the same face to the other. The surface itself holds its own mysteries that Webb's data is now helping researchers reinterpret. In a region named Tartarus Dorsa, New Horizons photographed something no spacecraft had ever documented anywhere else in the solar system. Tall, jagged blades of frozen methane ice, some reaching more than 1,500 feet high, arranged in long parallel ridges across the landscape. Similar, but far smaller formations exist here on Earth in certain high-altitude deserts, where they're known as penitents and rarely grow taller than an average person. A 2025 reanalysis of the original New Horizons data suggests these towering ice blades may wrap around as much as 60% of Pluto's equator, forming an entire ring of jagged frozen terrain circling the dwarf planet. South of the famous pale heart-shaped plain, two enormous isolated peaks rise out of the surrounding landscape, and researchers still can't fully explain them. One stands roughly 13,000 feet tall. The other may reach close to 20,000 feet, with a base wide enough to rival some of the largest volcanoes on Earth. Both mountains have deep depressions at their summits, ringed by fractures with lumpy, uneven flanks that closely resemble cooled lava flows, except there's no molten rock anywhere on Pluto. If these features are what they appear to be, they're cryovolcanoes, structures that once erupted, not with melted stone, but with a thick slurry of water, ammonia, and methane forced upward from somewhere deep beneath the icy crust. That internal warmth leads directly to one of the most debated ideas surrounding Pluto today: the possibility of a hidden ocean buried roughly 100 miles beneath the surface, kept in a liquid state by the slow radioactive decay of elements inside Pluto's rocky core. The evidence isn't a photograph, it's a pattern. Cracks and ridges across the surface line up in ways that fit what you'd expect from a subsurface layer of liquid water, shifting slowly beneath the crust. And that famous heart-shaped plain sits directly above what appears to be a gravity anomaly, a spot where something denser than the surrounding ice may be concentrated underneath. Similar hidden oceans are already strongly suspected beneath the icy surfaces of Jupiter's moon, Europa, and Saturn's moon, Enceladus. If a body as small and cold as Pluto turns out to be, hiding something similar, it would suggest that buried oceans might be a far more common feature of icy worlds throughout the outer solar system than scientists previously assumed. Right now, there's no way to confirm any of this directly, and there's currently no funded mission planning to send a probe back to Pluto, no lander, no orbiter on the books. Missions to the outer solar system are extraordinarily expensive and extraordinarily slow, often requiring a full decade or more of travel time before a spacecraft even reaches its target. For the time being, Webb remains our only working tool, quietly checking back in on Pluto every few months whenever it swings back into view, adding another data point each time, and almost always making the overall picture stranger than it was before. Here's the detail that tends to stick with people longest after hearing this whole story. Pluto sits inside the Kuiper Belt, a vast ring of icy debris beyond the orbit of Neptune, home to hundreds of thousands of objects and an estimated trillion or more comets. A handful of other bodies out there, including Eris and Makemake, come reasonably close to Pluto's size. Beyond the Kuiper Belt entirely lies the theorized Oort cloud, thought to hold another trillion or so icy bodies. Only one spacecraft, New Horizons, has ever ventured deep enough into that region to closely photograph any of its larger residents. And even that mission only managed close flybys of 2 objects out of the hundreds of thousands of similarly sized worlds believed to exist out there. If Pluto is genuinely cooling its own sky, slowly bleeding its atmosphere onto a companion moon, and possibly hiding a liquid ocean beneath a shell of solid ice, there's no obvious reason to assume it's the only object out there doing anything like this. It's simply the one close enough and bright enough for our current instruments to study in real detail. Nearly everything else scattered across that same enormous region of space remains almost entirely unobserved. So what does all of this actually add up to? James Webb wasn't built with Pluto in mind. It was designed to study the earliest galaxies in the universe, and yet it ended up solving a problem that had frustrated planetary scientists for decades, teasing apart 2 overlapping worlds 4 billion miles away and revealing a climate system nobody expected a dwarf planet to have. Out past the orbit of Neptune, in the cold and the dark, there are trillions of other worlds we've barely glanced at, let alone studied closely. And if one small, formerly dismissed dwarf planet was hiding this much complexity beneath its surface, it's genuinely worth wondering what all of those other distant worlds might be hiding too. If stories grounded in real published research are what you want more of, subscribe to this channel and turn on notifications, because Webb is still pointing back at Pluto every few months. And there's a real chance the next round of data adds another genuinely strange piece to this puzzle. And the strangest part of all might be this. Every one of those data points is coming from an instrument that was never designed with Pluto in mind at all, quietly proving, almost by accident, that it can still teach us something new about our own solar system's furthest edge. Thanks for watching, and I'll see you in the next one.